Alright, good morning everyone. I know you're probably not super excited about the idea of having to do this lecture, but we have to keep up with notes, so bear with me. Alright, so we'll start. This is note set 2 notes. We'll not get through all of this today, but I will finish going over it on Friday. First, I'm going to start off with a clarification for AC versus DC. Of course, we said that AC current flows back and forth, changing the direction many times per second. So to get a visual of what this looks like, here's a mechanical system. You have a piston and crank here. So think of this as moving back and forth, right? So that means that sometimes the current is going to flow in this direction, and sometimes the current will flow in the other direction. Now, this is what's supplying the power, which is forcing this to move back and forth, while this pinched off section of the pipes is representing resistance. So one important thing to note here is that there will be some resistance in the water flow no matter which direction it's flowing. So when this moves forward and the water is flowing in the counterclockwise direction, then you'll have the same resistance as what you have when you're dealing with when this moves forward and the water's flowing in this direction. Alright, so also just a clarification, quick example for DC. We said that the current flows in one direction all the time at a constant value. So visual representation of this is if you have a tank of water and you have a single pipe, so it's only a unidirectional flow, would be going out of the pipe. Right. So now we're going to start constructing circuits, but before we do that, we need to start with another term and then also introduce one of the first laws that we will be using throughout the semester. For circuits, we'll start with resistance. Resistance is defined as the physical characteristic that causes electrical energy due to current flow to be converted to thermal energy. Now, if if enough heat, or if the heat gets too high, actually what you'll have is a conversion to light energy as well, but we won't really worry about that here. The units we use for resistance are ohms. I believe we discussed this previously. So now that we've discussed that, let's introduce Ohm's law, where Ohm's law is defined as the voltage across a resistor is directly proportional to the current that's through it. Right? So Ohm's law states that any voltage across a resistor, there's a direct proportionality between it and the current flowing through that resistor. Just to show a couple of representations or notations for how we define this is exactly this. So when you have voltage, which is arbitrarily choose plus to minus, then if you have some resistor and you're talking about the voltage across it, the current through it is entering positive. Okay, and by Ohm's law, this means that V is equal to I times R. So voltage is equal to current times resistance. Another notation for this is just, with a voltage source. If you have a voltage source directly across a single resistor, then the current flow is going to be going through the resistor because the voltage across this resistor is plus to minus. We'll make note of this in a moment about this notation. Another way to define voltage and current is to name the nodes. Again, we'll talk about nodes later, probably on Friday. But if I were to name the point on either side of the resistor, I call this A, call this B. then if I'm saying from plus to minus or from A to B, the voltage VAB would equal to the current flowing from A to B, IAB, times the resistance. So all of these mean exactly the same thing. Alright, so it's important to note again that both the picture and the equation are necessary. And the reason this is necessary is because of passive sign convention. Okay, so this is really, really important, and a lot of people get confused with this notation. So you really want to make sure you have a hand on it now. Alright, passive sign convention states that the current flows into the positive terminal, or positive side, what we'll later call a node, of the defined voltage. Alright, so we said in the previous slides that, the voltage is defined as plus to minus and the current is entering the positive. That's exactly what we mean with passive sign convention. When we're talking about this, we're talking about passive elements. So you'll note in this picture, for example, if you look at it with regard to a voltage source, and then you would think of it as the current's leaving this source. So this is actually going to be, so this is a source and this is a passive element, so active versus passive, and we'll make a note of this when we talk about power. Okay. So modeling, now that I've kind of shown you what some of the circuit elements look like, some of the assumptions that we're going to be making. Now, lumped elements, when I'm talking about this, I'm referring to resistors, capacitors, and inductors. Again, we're just going to start out with talking about resistors. Actually, that shouldn't be up there with the ideal sources. That should be with ideal sources, not with the ideal conductors. Alright, so ideal conductors, so this is really talking about, I forget what exactly I wanted to mention here, so I may have to go back to this on Friday when I look at my notes. But I mean, ideal conductors, what I think of with this is I think of zero resistance, right? So I'll come back to this on Friday. But really, what I think I'm leading into here is that with ideal sources, what I'm looking at, in our case, what we will be discussing throughout the semester are ideal voltage sources and ideal current sources. Now, it can be sort of aggravating because there's no such thing as a current source in real life, right? You can't go to the store and buy a current source. But voltage source, you think of a battery, that is exactly what we're dealing with. We use current sources when we're looking at circuit analysis just to discuss, okay, hey, there's a specific current here, and we can easily represent it with a current source. Note that for these sources, when I talk about ideal sources, I'm saying that I'm assuming this is a perfect source, and whatever value I'm given for the voltage or the current is exactly that, right? So normally, like with an actual source or a non-ideal source, you actually have some resistance that is in series with the source. So in our case, what we're going to say is whatever source value is given to us is exactly what value we're going to be using. All right. Again, note, so when I talk about sources, I'm not using passive sign convention because the voltage, right, I have the current leaving the positive instead of entering. And for this, I have the current leaving the positive terminal that I've defined the voltage across here, right? So not quite what we previously discussed, but what this has to do is with DC power. And again, we're about to discuss that after I get into a couple of examples for Ohm's law. Okay, so right now, as we get into these examples, what's important is, okay, how is the voltage and the current defined with respect to the resistor, or with respect to the passive element, right? So first off, first Ohm's law example, we have a voltage source that's connected in series with a resistor, right? And we're asked for the current that's flowing, and so these are defined, and what we're going to do is solve for these values based on how they're defined, okay? Now, we said that, previously when we looked at the definition for Ohm's law, the notation for passive sign convention, we said that, okay, if there's a voltage source that's directly across this resistor, that means that the voltage across the resistor is plus to minus, top to bottom, based on this source. If this source were plus to minus, then the voltage across this would be plus to minus. Now, that's not the case here, so we're assuming plus to minus. And if we talk about the voltage across this resistor, then the current should be entering the positive. So this is the correct notation for how I would say a positive current would flow, all right? So what I have is, using Ohm's law, that V is equal to IR, therefore I is equal to V over R, which means that I is 5 amps based on how it's defined here, okay? Our next example, say this little cloud is just representing some other system, but we know across this system, or between these two nodes or two sides or two terminals, that the voltage is plus to minus 10 volts, right? So this is opposite of how we defined our previous example, okay? So based on this notation, that means that, okay, there's nothing else here and just the resistor, so that means I know the voltage across the resistor is on the bottom plus to minus, right? So plus on the bottom, minus on top is 10 volts. Now this time I'm saying that means that the current is entering the negative. So this is opposite of how my passive sign convention is defined, right? And again, we're solving for current defined as how it's defined, not by how it's actually flowing. But if I wanted to, I could redraw the circuit so that everything looks how I would expect it to for passive sign convention, right? So that would mean that I would redraw this circuit looking across the resistor. I could swap the sign of the voltage so that the top is positive and the bottom is negative. So that would mean I'm dealing with a negative 10 volts across the resistor. So that by swapping this, that means the current's entering the positive across the resistor, right? So that meets passive sign convention. And again, I can use Ohm's law and say I is equal to V over R. And this time I get negative 5 amps. So what's going to be really important with passive sign convention is it not only tells us what the magnitude of the voltage or current is, it's also telling us what direction it's in based on how it's defined. Now, if the current were defined in this original circuit going in the opposite direction, then this would have been a positive 5 amps based on how the current is defined. Alright, so let's look at another example of this. Right, so we're dealing with a source, and this source is across this resistor, so that means the resistor has plus to minus 10 volts across it. Now, in this case, IA is defined as leaving the positive of the resistor, right? So based on this, right, passive sign convention is not met because we said current should enter the positive terminal for the voltage across the passive element. So if we redefine this, say I redraw the circuit and I just swap the direction of the current, and instead of calling it I naught, I call it IA. So what happens is, okay, so based on the second circuit, this meets my passive sign convention notation, which means that I get a positive 5 amps. Now, IA with respect to I naught is just a change in direction. So that means that from our original circuit, I naught is equal to negative IA, which means I naught is equal to negative 5 amps. Right? Bear with me, just a few more examples. Right? So now we've got another example, okay? And this one you have to pay really close attention to because this source, right, which is also the voltage across this resistor, is plus to minus, so top or bottom to top, plus to minus, negative 10 volts. So that would also be the same as me swapping this and saying plus to minus across the resistor, plus on top, minus at the bottom, positive 10 volts, right? So let's look at what that is. Okay, so when I change that, plus to minus is negative 10 volts. I could swap the voltage, but actually what happened here is change the direction of the current, right? So that's the other option, because if I look at this based on the source, and this is minus to plus, the current, right, is entering the positive. Okay, we can handle that. So to redraw this, again, this is actually the same direction, so it's still flowing counterclockwise, right? So it's entering the positive, which is correct based on passive sign convention, which means that our current is just negative 10, just because the voltage is defined as negative 10 volts from bottom to top, right? With the current entering the positive, and that means our I naught as it's defined is negative 5 amps. Now, if this I naught had been defined in the opposite direction, then what we would have gotten is positive 5 amps. Again, we're solving for the value, so you'll get the magnitude right if you use Ohm's law correctly, but really what's important is you're solving for the value of the current or the voltage based on how it's defined, which may not necessarily be how it's actually flowing. Okay, so one more example. Now we're going to throw out a current source, right? So in this case, we've got 10 amps flowing in the clockwise direction. And based on this and how the voltage across the resistor is defined, the current would be entering the positive of the voltage. So that meets our passive sign convention notation. So based on that, well, there's only one current flowing. This current times this resistance using Ohm's law is going to give us a voltage, V naught, or yeah, so that should be V naught here, equal to 20 volts, right? So those are just a few examples just to toy with and really hopefully get an understanding of what passive sign convention means when it comes to looking at the voltages across and the current through a resistor or a passive element. Okay. Last topic before I end today, I'll start with the time domain of power, right? So we previously discussed power. We talk about time domain, it's P as a function of time is equal to the voltage as a function of time times the current as a function of time. So we're not really going to worry about time domain currently, just because we said we're starting with DC values, which we said were constant over time. Really what we want to look at is our DC circuit's power, which is P is equal to V times I. Now the units for these are watts, as we previously stated. Okay. So here's going to be some clarification on why the sources, the direction of the current based on source, voltage, and current notation is different than what we previously stated for the passive sign convention, right? So one of these is going to match up with what we said for passive sign convention. The other one is meant primarily for anything that's a source, which means it's supplying something, right? So if we say power is supplied, right, if we're asked for what power is supplied for something, then the following notation is used, right? So what we're dealing with here is, okay, this is the opposite of what we said passive sign convention is, because for supplied notation, this is the current leaving the positive, right? Or you can think of it as the current entering the negative, okay? So this is exactly what, normally we say that a source supplies power, right? So this is the notation that you would assume for that, okay? Or anytime anything is stated as power supplied. So again, this box right here is just representing some element, right? again, primarily we're talking about sources, but there are some circuit setups where we can say, something else is supplied, but we'll talk about that more once we get into other examples, and we'll have some power examples starting on Friday. Right, so again, P is equal to V times I. So when I solve for that P based on that voltage and current definition, then that I would say is supplied power. Now, if the power absorbed is asked for, use the following notation. It's the same notation that we had for passive sign convention. So this box here representing some element we'd normally say is, okay, that's some passive element, which for now is what we're talking about with resistors. Right? There may be some cases where you have multiple sources in a network and one source overpowers the other and a source may be absorbing power. But primarily, this is what we're referring to. Okay. Again, P is equal to V times I, and based on this notation where the current enters the enters the positive, the voltage, or leaves the negative, we're talking about power that is absorbed. Okay. Now, again, I say we talk about power absorbed for a resistor. Again, resistors, we use passive sign convention when we're talking about it. So really what I'm saying with passive sign convention is if I define a voltage or a current, well, let me start with the example of defining a voltage. If I were to define a voltage, right? So for example, in this case, I said plus to minus from left to right. Then that means, based on passive sign convention, I would define the current as entering the positive. Okay? Now, if I just define the current this way, going from left to right, then based on passive sign convention, I would write the voltage as plus to minus. Right? So if you're given one of them, the direction, then you know the direction for the other one. Okay? So shortcuts for saying power that's absorbed by resistors. If we know the voltage across and the current through a resistor, then based on that and knowing Ohm's law is V is equal to I times R, if I substitute in for V into this power equation up here, then I can also say that the power that's absorbed by a resistor is the current squared times the resistance. Right? So all I'm doing here is taking this V is equal to IR, Ohm's law, plugging V in up here. So plugging IR in for V here, and I get P is equal to I squared times R. Or you could also solve for this another way. Again, power equation is voltage times current, but we can also state Ohm's law. Instead of saying V is equal to IR, we could solve for current and say that's equal to voltage over resistance. So based on this, if I plug in V over R for I up in this equation, then what I get is P is equal to V squared over R. Okay? So these are just a couple of shortcuts for finding power absorbed by a resistor. Alright, so that's all I have for today. I'll answer any questions on Friday, and I'll go over examples of this power absorbed versus supplied notation and what it means when you're asked certain problems.